Welcome everybody. This is 9.7 Marginal Analysis. So marginal is just another fancy word for derivative. Okay. So we want to find marginal cost, revenue, and profit functions. And the definition of that is the instantaneous rate of change, or the derivative, of cost, revenue over profit relative to production at a given production level. Meaning that, remember that the derivative finds a slope at exactly 1 point. So if we want the marginal revenue at X amount of items, we want to know, is our revenue, cost, profit increasing or decreasing at a certain value of X? So that's all this marginal stuff is. Okay. So go over some functions really fast. Cost is always known as C of X. Marginal cost, which is the derivative of the cost function, is known as C prime of X. Average cost, which is C bar of X, is given as C of X over X. And then there's marginal average cost, which is the derivative of average cost, which is C bar prime of X. Yes, C bar prime. Great, right? Okay. And then next is revenue, which is R of X. Marginal revenue, R prime of X. Average revenue, R bar of X over X. And marginal average revenue, R bar prime of X. Whoa. All right. Profit is P of X, which is given by R of X minus C of X, revenue minus cost. Marginal profit is the derivative, P prime of X. Average profit, P bar of X, and marginal average profit, P bar prime of X. Whew. Just so you know what to do in case any of the questions ask you, what is the average profit, marginal average profit? Okay. All right, first theorem we come across is something called marginal cost and exact cost. The exact cost formula, so let's say you want to find the exact cost of one item. Well, you will do C of X plus 1, so the X plus first item minus C of X. So if I was given, if we were told, find the exact cost of the, of the 51st item, I would plug this into the cost function as C of 51 minus C of 50. I would do C of 51 minus C of 50 to find the exact cost of the 51st item. Okay. And then marginal cost says the marginal cost approximates the exact cost of producing the X plus first item. And that formula is given by the derivative. The C prime of X, the value of C prime of X is approximately close to the value of C of X plus 1 minus C of X. So if I go with the example I wrote earlier, if I said C prime of 51, the derivative of that number would be very close to the exact cost of C of 51 minus C of 50. That's it. And we'll be off by some change or maybe a couple dollars. Who knows? We'll see when we get to the examples. And this doesn't just have to go for cost. It can go for revenue and profit as well. Okay. So, example 1, let's try out exact cost and marginal cost. So a company manufactures fuel tanks for cars. The total weekly cost in dollars of producing X tanks is given by C of X equals 10,000 plus 90X minus 0.05X squared. So for A, to find the exact cost of producing the 501st fuel tank. All right, so what we do for A is we will say, for A, if we want to know the exact cost of the 501st fuel tank, we'll say C of 501 minus C of 500. This uses the exact cost formula. And what we're going to do is take these numbers and plug them into X into the function C of X. So essentially, it's calculator time now. So let me see if I can do that up here. Boom. And I will use, sure, I'll use this one. Let me just get situated. All right, clear, clear, right, table, clear. All right, let me type in this function that we see. 10,000 plus 90x minus 0.05x squared. Enter, 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 enter. And now I'm going to type in 501. And I'm going to type in 500. And let me write down those values. So we will get, at 501, I get $42,539.95. Minus at 500, we have 42,500. And this means when you subtract the two, the exact cost of 42,539.95 minus 42,500 is going to be 39.95. That is the exact cost. Okay, come back to the calculator in a second. So this is A, the exact cost. That's all we have to do. And now for B, it says, what is the marginal cost? So if you ever see the word marginals, all that says is, hey, take the derivative and plug in the number. So for B, first thing to do is to take the derivative. C prime of X. And the derivative of 10,000 is 0. The derivative of 90x is 90 minus the derivative of 0.05x squared. That 2 comes down. I have 5 cents and I just doubled it. So I get 0.10x as my derivative. All right. And all we have to do now is plug in 501. And I'll just do that in my calculator here. 90 minus 0.10 times 501. And we get 39.90. And this is the marginal cost, or approximate cost, right? Which we said from the theorem above that the marginal cost is going to be approximately equal to the exact cost. So just look at the difference between those. We were off by 5 cents. And most of the time, it's always going to be off by some change, by $1, anything like that. Okay. All right, and that's exact cost. That's marginal cost. Let's move on. Two, the total cost of producing X bicycles is given by the function C of X equals 10,000 plus 150X. Find the average cost per unit if 125 bicycles are produced. So we're just looking at average cost. Go back up. Average cost is given by C bar of X, which means it puts the cost function over X. So that's what we're using there. So back down. So the average cost is given by C bar of X, which takes the cost function of 10,000 plus 150X and puts it all over X. That's it. So there's the average cost function, and now it wants to know what is the average cost if we produce 125 bicycles. So what we do here is say C bar of 125 and have 10,000 plus 150 times 125 over 125. And I guess calculator time, right? Just to show you. Glad it just keeps that. The way I wrote it there is the exact way I'm going to type it in. Fraction button, 10,000 plus 150 times 125 over 125. And enter. And we get $230 is the average cost per bicycle if we produce 125. Or the average cost at 125 bicycles. All right, back. So average cost per unit of 125 bicycles are produced. When we produce 125. Okay. Next says, find the marginal average cost at a production level of 125 units. So take the derivative of the average cost function and plug in 125. That's all this one says. So we want the marginal average cost function, the MAC, all right, which means marginal average cost function, we're looking for C bar prime of X, right? We're looking for C bar prime of X. Well, before we begin, we must take our average cost function from above, C bar of X, which is 10,000 plus 150X over X, and we must algebraically rewrite it because we cannot take the derivative in this form. So this is just like 9.5's lesson. We have two terms in the denominator, which means we split it into two fractions. $10,000 over X plus 150X over X gives me zoom in here. 10,000x to the negative 1 plus 150. And now we will take the derivative of what we found at the end. We'll take the derivative of 10,000x to the negative 1, which means we're going to look at c bar prime of x. And the derivative of 10,000x to the negative 1 becomes negative 10,000 x to the negative 2. Derivative of 150 is 0. So there's our derivative. And now all we have to do is plug in 125. So c bar prime of x is going to be c bar prime of 125 is going to be negative 10,000 times 125 to the negative 2. And let's see what we get. And once again, just how I wrote it there is how I'm typing it in the calculator. Negative 10,000 times 125 raised to the negative 2. And we get negative 0.64. So we get negative 64 cents. Okay. Interpret the results. What does this mean? Well, remember, marginal is the same as derivative. And if our answer comes out positive, this means the marginal average is increasing. Or if our answer comes out negative, this means the marginal average cost is decreasing. The answer we got was negative, right? So this means that at a production level of 125 bicycles, the average cost is decreasing by 64 cents per bicycle. So we could say average cost decreasing. Average cost decreasing by 64 cents per bicycle. Okay. And then next says, use the results from A and B to estimate the average cost per bicycle if 126 bicycles are produced. Okay, well, right now we know that after 200, or at 125 bicycles, we're doing 230 per bicycle. Also, at 125 bicycles, the cost is decreasing by 64 cents. So all you really have to do here is take the answer from A, which is $230, and add it to the answer from B, which is negative 0.64 cents. And let me put a dollar sign there, sure. And the estimated average cost of the 126 bicycle is just going to be $229.36. Because if the cost is decreasing per bicycle, then the 126 bicycle is going to be 64 cents less than the last one. So that's it. So this would be $229.36. So this is the average cost of the 126th bike or bicycle, right? All right, excellent. Let's see, 10,000 plus 150x over x. Yeah, cool. I guess if you want to verify that step, just come back to the average cost function above. So it is fraction 10,000 plus 150, but this time I'll multiply in that 126 of what we're doing below over 126, and we should get the same result that I got in C. Hopefully. I hit enter, and it gives me that fraction. Great. All you have to do to change that to decimal is hit the little double arrows above the enter button. And bam. 229.36, which is exactly what we got for C. Okay, not bad. And makes a great connection for us, right? Lets us know that we're doing it correctly. All right. Hey, look at that last one, the long one. All right, we're probably gonna have to use a graphing program for this one. All right, a company's market research department recommends, recommends the manufacture and marketing of a new headphone set for Apple and Android phones. After suitable test marketing, the research department presents the following price-demand equation. X equals 10,000 minus 1,000 P, where X is the number of headphones that retailers are likely to buy at price P per set. The financial department provides the cost function. C of X equals 7,000 plus 2X. 7,000 is your fixed cost, tooling and overhead, and $2 is the estimate of variable cost per headphone set. Materials, labor, marketing, transportation, all that lovely stuff. Okay, so in the price demand equation, the first equation given above, express the price P as a function of the demand X and find its domain of the function. So to put it in English, solve this equation for P. Solve for P. That's all it says. All right, I can zoom in a bit. Let me put X equals 10,000 minus 1,000 P. Okay, we're going to solve this for P. So the first thing to do is move that 10,000 over. Minus 10,000 minus 10,000, and we get X minus 10,000 equal to negative 1,000 P. And then next, divide everything by negative 1,000. All right. Then this, come over here. You'll get negative X over 1,000 plus 10,000 over 1,000, that is just 10, equal to P. Now, 1 over 1,000, we want to change this to decimal. This is going to become negative 0.001, right? 001 X plus 10 equal to P. We have now solved or expressed the demand equation in terms of P. So that's the first answer. The next answer is to find the domain of this function? Well, we have to piece some things together here. How do we find the domain? What are we messing with here? We're messing with price, right? It says find the domain. Oops. Find the domain of this price function. Well, what do we know about price? Can price ever be negative? Do we want the price of our headphones to ever be negative? And that answer is no. So to find the domain of this function, we take our price equation here. We take price and set it greater than or equal to 0. Yes, price can hit 0 because sometimes we give things away for free to market, right? So we can say equal to 0. And now what I'm going to do is plug in my actual price equation that you see here, negative 0.001x plus 10. Set it greater than equal to 0, right? That just comes here. And solve it for x. So move that 10 over. And then divide by 0.001 by negative 0.001. And I still got room. Okay. And remember, whenever you multiply or divide by a negative on an inequality, the inequality will always switch, right? So we'll get positive x has to be less than or equal to, and 10 over 0.001, I believe, is 10,000. Let me just make sure. Yep. That's 10,000. Okay. So the last thing we have to do is piece it together. And this is going to be a double inequality, or what they call a compound inequality, because the first piece of the inequality started up here. Price had to be greater than 0. And now, well, we can't price them at 10,000 headphones, but so price has to be greater than 0, and we have to stay less than or equal to 10,000. So this is finding the domain of the function. Okay, so if we piece this together, the actual domain says that we must stay above 0 and stay less than 10,000. So here is your actual domain. 0 to 10,000. So this means that our headphones must stay between 0 and 10,000, and it also says that our price must stay above 0 because we can never go negative. So that one's done. We have solved or expressed the equation in terms of price, and now we solve for its domain. So in order for the revenue, cost, and profit function to make sense, our domain has to stay between 0 and 10,000. Okay. Now this says, B, find the marginal cost function. So all this wants is the derivative of the cost function. That's all this wants, and it's done. Find the marginal cost function. Well, we may want to state what it means to interpret at least, right? So there's the cost function up there. So the marginal cost function, which is just c prime of x, the derivative. Well, what's the derivative of 7,000? 0. What's the derivative of 2x? 2. And there it is. That's all it wants. But again, what does it mean? Well, remember the derivative gives you the slope of the function. Well, look, the slope of this function was 2. Is that not our derivative? 2? So all this means is that the marginal cost function is telling us no matter what, the price of each headphone is still increasing by $2, as stated in the actual problem, right there in this paragraph. $2 is the estimate of variable cost per headphone. So no matter what, we are still, it's $2, price increases, or not price, cost increases, $2 per headphone. That's all this says. Right. I mean, I could write that in there. Why not? All right. Find the revenue function and state its domain. Okay, it wants us to find a revenue function. So remember that revenue functions are always made of the number of items times the price that we sell them at. Okay. Well, this means that to create a revenue function, we need a price function or a price equation. And do we have one of those already? We sure do. R of x equals x times p. Our price equation is what we found in A. Look at that. There it is. There's the price equation. Plug all of this in for P. That's all we have to do. So you'll get x times negative 0.001x plus 10. Distribute the x, and you'll get negative 0.001x squared plus 10x. There is the revenue function. That's revenue. Okay. And domain, well, guess what the domain's going to be? If this is domain for the price, headphones, cost, and profit, this is also going to be the same domain for the revenue function. Why should it change? It should never change. It should always be the same. So our domain for revenue is still 0 less than or equal to x less than or equal to 10,000. So it's the same domain as that. Okay. Should not have different domains for functions that are related. So everything's related here. Okay. And then find the marginal revenue function and plug in the numbers 2,000, 5,000, 7,000, and interpret the results. All right, so this means to take the derivative of the revenue function we just found, take the derivative of this function, and plug in 2,000, 5,000, and 7,000. So first thing, let's take the derivative of that revenue function. R prime of x, the derivative of negative 0.001x squared should be negative 0.002x. And then the derivative of 10x is 10. So plus 10. There we go. And now evaluate it at 2,000, 5,000, and 7,000. So let me do this. R prime. That's 7,000. Okay. Calculator time. Let me type this function into my table. Makes things a lot faster. Negative 0.002 x, right? 0.001 times 2. Okay. Negative 0.02 x plus 10. Enter, 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 and then I'll type in my numbers. 2,000, 5,000, 7,000. And we get 6, 0, negative 4. Okay, back to the notes. What does it all mean? Well, this means at 2,000 headphones, at 2,000 units, well, first off, is this answer positive or negative? This is positive. So this means at 2,000 units, revenue is increasing $6 per unit, right? Revenue increases. Then at 5,000 headphones, we have $0, right? We have $0. So this means we were first increasing, and now we're kind of plateauing, right? So this means at $0, we possibly are breaking even, right? So we can say revenue remains constant. And then last, at -4, so at 7,000 headphones, we are making now -$4 per headphones, which means that cost is now beating revenue, which means that we are not making any revenue. So we can say revenue decreasing, or we are just not getting any revenue in, right? This means cost has passed up revenue. So let me show you a visual representation of what we're looking at. So the cost function, or actually the revenue function, is looking something like this. And when X is, was it 2,000? This means at 2,000, at this one exact point, we are increasing by $6 per headphone. And then at, was it 5,000? We've reached the top. This means, and most likely this means that revenue and cost have met each other. We might be breaking even. This means we're not making any more money. And then at 7,000 headphones, the cost, actually the revenue is now decreasing, right? Revenue is now decreasing. So that's everything that we're looking at. And once again, I think my math lab wants it stated differently. So if it wants to know what's happening, you can say at, what is it? It's like 2,000 units, revenues. You can say revenues increasing. And then at 7,000 units, it's, I think it wants you to say that you are not making money at all. Like there is no money coming in because -$4, yeah, we're losing money because cost is now being revenue. But just let me know if you need help with those. It wants special wording. Okay. E, graph the cost function and revenue function on the same coordinate system and find the break-even points and indicate regions of loss and profit. So this one would take like 30 minutes to do. So I'm going to show you how to shortcut this, and it's fine as long as our graph is nice and labeled. So first thing I'm going to plot are the x values, and the x values are given by the domain. We are given x values to stay between 0 and 10,000. So that's what I'm going to do here. We'll say 0 and then 10,000. We can go by 2,000s. 2, 4, 6, 8, 10. And just make note that this is in the thousands. Y values, we'll get there in a second. We'll look at the graph I'm about to do. Okay, let me do this again, and then let's see. Do I have the browser open? Perfect. All right, what I'm gonna do is go to Desmos.com, one of the best graphing programs ever. Go to this graphing calculator, and then I'm gonna type in our functions. So let me, actually, first, before I do that, you can actually change the domain of this graph. So click this little tool icon on the right side, and down below here, let's see, I need that, and I'm gonna type in 0, and then I'm gonna type in 10,000. Did it do it? Nope. I can't see it because it's in the way. All right, let me try again. So this one is going to be 0. And now this one, there we go. So all I did was change up that x-axis to 0 and 10,000. Perfect. And now let me minimize this. You get over here, and I want view. And now I'm going to type in our revenue function, negative 0.002x. Oh, that's the derivative. Whoops. Nope, don't do that. The revenue function. There we go. Negative 0.001x squared plus 10x. Enter. And now I'm going to type in the cost function, because we want to graph revenue and cost. And I'm going to type in that function, 7,000 plus 2x. Enter. All right, and now I'm going to hide this menu on the left, and let's look at what we have. How high does this function go? I might have to change up these. Let me see. Oh, yeah. Let's try. So let me change my y-axis then. Oh, look at that. That's good. I'm going to say 0. And then here, let's try like, let's try like 100,000. Let's see what happens with that. Hey, that worked. Now we see that. Okay. Perfect. Maybe 100,000 is too big. Let's do 25,000 like it shows. Better. All right. Cool. So now, we know that over here on the right side, we're going up to 25,000. So let's just go by 5,000s. So again, let's label all of these. So I can go 5, 10. Actually, I think I can space it out. Let me see. $5, $10, $15, $25. Okay. And so we know that our revenue, our cost function is going to look something like this. I'll put cost as blue. So again, this is just a sketch. So there's cost, and then here's going to be my revenue function. And we know at these exact points, these are the break-even points. And to find those exactly, well, let's look back at the Desmos graph, and I'm going to click right where they intersect. Click that point and look at that beauty. So that means this point is 7,000 and 21,000. That's not it. And this point is, if I click down here, 1,000 and 9,000. And that's all you have to do to actually really graph it. So it's just a sketch. We didn't have to get in detail. Okay. And then we said indicate regions of loss or profit. So back to the notes. Well, remember that you have a loss when cost is greater than revenue. So down here, it's a good color, I'll just do green. Everything down here, actually green is good for money, so we'll do purple. Everything down here is a loss of profit, and everything over here is a loss of profit. And guess what? When revenue is greater than cost, everything in here is profit. So this green says we have profit gain. And purple is, of course, profit loss. Here and there. And that's it. I wanted to keep that one simple as possible. And when I say simple, I mean not using the quadratic formula to find break-even points, because that would have took a while, even though you know how to do that already. Okay. So we found the break-even points, and we found the regions of loss and profit. So purple on my graph was loss, green was gain. Okay. Moving on. F. Find the profit function in terms of X. All right. So now we want to find the profit function, and remember profit is given by revenue minus cost. So for profit, we have to enter the revenue function, which is right there, negative, I'll just zoom out, keep it simple, negative 0.001 x squared plus 10x minus the cost function, which was 7,000 plus 2x. And just simplify and solve for x. Make sure to distribute that negative. And we get negative 0.001x squared plus 8x minus 7,000. And there is the profit function. All right, almost there. Find the marginal profit and evaluate it at x equals 1,000, 4,000, and 6,000. So all you have to do is take the derivative of the profit function that we just found and plug in those numbers. So let's finish this up. So p prime of x is going to be negative 0.002x plus 8. There's the marginal profit function. And now plug in those numbers. P prime of 1,000, P prime of 4,000, and P prime of 6,000. All right, back to my calculator. And I can get rid of this. I can get this back. There we go. Type in my profit function, marginal profit function, negative 0.002x plus 8. And type in these numbers here, 1,000, 4,000, and 6,000. Hey, look at that. 6, 0, negative 4. All right, back to the notes. Finish this off, interpret the results. And at 1,000 headphones, we have a positive number, which means profits increasing, right? And then $0, which means profit is constant, which means we are breaking even with the cost function, right? And then over here, profit decrease, right? Profit is at a loss. And that's it. That is marginal analysis using derivatives, right? Using calculus. Oh, it's so colorful. Okay. Well, that is all. Till the next one.